Imagine a power generator that does not use diesel, does not burn natural gas, and does not require a connection to an electrical grid. Imagine setting it down next to a major regional hospital, pouring in salt water, and watching it supply uninterrupted electricity to every operating room, ventilator, and intensive care unit for 50 consecutive years. No refueling trucks arriving every 48 hours, no routine oil changes, no fear that a winter storm or a collapsed regional grid will suddenly turn off the lights in a life-or-death surgical ward. It sounds like a headline pulled straight out of a cheap science fiction novel, or an exaggerated internet rumor, designed to collect quick clicks. But right now, on the edge of the Gobi Desert in Gansu Province, Chinese state engineers have turned that exact concept into a physical, working reality. At a facility outside the city of Wuwei, a revolutionary energy generation platform is undergoing final operational testing. It represents a fundamental shift in how human beings create, store, and distribute critical power. To understand why this moment has sent shockwaves through energy departments in Washington, Tokyo, and London, you first have to separate internet noise from actual engineering science. Social media posts describe a magical box where simple ocean water goes in and infinite electricity comes out. That is not what is happening. The reality is far more interesting, and strategically, far more dangerous for incumbent energy giants. What Chinese scientists have actually built is a dual-system power platform that combines two breakthrough technologies. The first is a commercial-scale liquid molten salt reactor that uses liquid salt matrices to generate massive thermal energy without needing millions of gallons of cooling water. The second is an advanced aluminum-seawater electrochemical backup array that sits completely dormant until it comes into contact with salt water, instantly starting a chemical reaction that yields high-output electrical current for critical facilities. Together, these systems solve a problem that has haunted power engineers for over a century. How do you build a zero-maintenance, completely off-grid power source that never degrades, never relies on atmospheric weather like wind or sun, and can run an entire hospital complex continuously for half a century? The average American emergency generator at a local hospital can run for roughly 48 to 72 hours before its diesel tanks dry up. The system sitting in Gansu is built to run until the year 2076. When American energy analysts first looked at the preliminary test data coming out of Wuwei, many assumed the figures were overstated. Western power grids have spent decades relying on the same basic formula: big power plants connected to miles of high-voltage transmission lines, backed up by noisy, pollution-heavy diesel engines inside facility basements. The Chinese project ignores that playbook entirely. By marrying liquid salt thermal technology with seawater-activated chemical storage, they have unlocked a way to make critical buildings entirely sovereign from the national power grid. This is not just about a clever piece of hardware or an impressive university experiment. It is about what happens when an entire country decides to redesign emergency power from scratch. By the time you finish this story, you will see that the race for the next 50 years of power is not being decided by who can build the biggest solar farm or the quietest wind turbine. It is being decided right now by who can harness the strange, untapped physics of salt water, and the consequences for American technology, healthcare, and national security are far bigger than anyone in Detroit or Silicon Valley expected. To see why China's 50-year saltwater power breakthrough is sending shockwaves through Western engineering labs, you have to look at what happens inside an American hospital when the power grid goes down. Most people assume that medical facilities operate on unshakable, bulletproof backup systems. We see the sleek glass towers in cities like Houston, Chicago, or Miami, and assume their power systems are built for the future. But the reality under the hood is a dirty, dangerous secret that the healthcare industry rarely talks about out loud. When a severe storm hits, a heat wave overloads the transformer lines, or a winter freeze paralyzes local infrastructure, American hospitals rely on technology that has barely changed since the 1950s: massive, subterranean diesel generators. These machines are loud, expensive to maintain, and remarkably fragile. More importantly, they run on a clock that starts ticking down the very second the main power grid collapses. an average 500-bed hospital in the United States consumes as much electricity as a small town. To keep its surgical suites illuminated, its life support ventilators pumping, and its organ storage refrigerators cold, a hospital's backup generators burn through hundreds of gallons of diesel fuel every single hour. Most facility basements store enough fuel on site to survive for just 2 to 3 days. After 72 hours, if the municipal grid is still dead, that hospital is forced to enter a state of total crisis. It must line up continuous fleets of fuel tanker trucks to navigate flooded roads, cleared debris, or blocked highways just to keep its patients alive. We do not have to guess what happens when that fragile logistical supply chain snaps. We have already lived through it. During Hurricane Katrina in 2005, backup generators at Memorial Medical Center in New Orleans failed when rising floodwaters submerged the fuel pumps and overwhelmed the lower floors. Doctors and nurses were left fanning critical patients by hand in dark 90-degree hallways as basic medical equipment turned off one by one. 7 years later, when Hurricane Sandy slammed into New York City, Bellevue Hospital and NYU Langone had to evacuate hundreds of patients, including intensive care infants, in the middle of a storm because their basement fuel systems flooded and their emergency generators failed. Even when extreme weather is not involved, the financial burden of maintaining these ancient diesel systems is staggering. U.S. hospitals spend billions of dollars every decade performing mandatory weekly testing, replacing degraded fuel, repairing rusted exhaust pipes, and purchasing emergency insurance policies. Diesel fuel degrades inside storage tanks after just 12 months if it is not constantly treated with chemical additives. If an unexpected power outage strikes and the stored diesel has turned to sludge, the generator engine seizes, leaving the entire facility in pitch darkness. This is the exact vulnerability that Chinese engineers set out to eliminate. They looked at the inherent weaknesses of Western critical infrastructure, the finite fuel supply, the constant mechanical maintenance, the short battery lifespans, and the total dependence on clear roads during a crisis, and asked a radical question. What if a hospital's backup generator required no fuel trucks, no moving engine pistons, no chemical fuel stabilizers, and could sit completely untouched for decades until it was needed? That question is what drove the development of the Gansu liquid salt matrix and seawater-activated power platform. While American healthcare administrators spend millions every year maintaining 48-hour diesel tanks, Chinese developers built a system designed to deliver continuous off-grid electricity for 50 years straight without a single drop of petroleum. And to understand how they pulled off an achievement that Western engineers claimed was physically impossible, you have to look at the unique, mind-bending physics of liquid salt itself. To understand how a saltwater power system can run an entire hospital for 50 years without stopping, you have to throw out almost everything you think you know about standard power generation. Most traditional power plants, whether they burn coal, natural gas, or use traditional nuclear uranium rods, operate on a surprisingly old-fashioned principle: boiling tap water to create high-pressure steam that spins a heavy metal turbine. Water sounds simple and natural, but in high-energy power generation, water is actually a complete nightmare to manage. Water boils at a relatively low temperature, 212 degrees Fahrenheit. To get water hot enough to produce the massive thermal energy needed to run a giant industrial generator, you have to squeeze it under extreme, unnatural pressure, often more than 100 times the atmospheric pressure of the air around us. That intense pressure requires giant, ultra-thick steel pressure vessels, massive cooling towers, and thousands of miles of high-pressure piping. If a single valve leaks or a pipe cracks under that pressure, the water instantly flashes into expanding steam, causing catastrophic explosions or system meltdowns. It is why standard nuclear plants require millions of gallons of fresh water from nearby rivers or oceans every single day just to keep their systems from overheating. This is where the genius of liquid molten salt changes the entire thermodynamic equation. When you take specialized industrial salts, like fluorine or chlorine compound salts, and heat them up past their melting point, they transform from solid white crystals into a clear, glowing, free-flowing liquid. And that liquid salt behaves completely differently than tap water. First, liquid salt does not boil until it reaches nearly 3,000 degrees Fahrenheit. That means you can run a liquid salt power system at extremely high, hyper-efficient temperatures without building up high pressure inside the pipes. The liquid salt flows through the heat exchanger at normal, ambient atmospheric pressure. You do not need giant steel pressure domes. You do not need massive cooling towers filled with ocean water. You do not need complex, fragile, high-pressure pumps that can blow a seal and shut down an emergency system. If power cuts out or a pipe develops a seam crack in a liquid salt system, there is no high-pressure steam explosion. The liquid salt simply cools down as it hits normal room air, solidifying back into harmless, solid rock salt right where it sits, instantly sealing the breach itself. It is a self-stopping physical safety mechanism built directly into the laws of chemistry. Furthermore, liquid salt possesses an extraordinary thermal capacity. It holds onto heat like a sponge holds onto water. A compact loop of hot liquid salt can store and transfer thousands of times more heat energy than the exact same volume of pressurized steam or high-temperature gas. This allows engineers to shrink the physical footprint of the entire generator system dramatically. A traditional water-cooled power facility requires acres of heavy real estate and continuous industrial water pipelines. A liquid salt generator can be engineered down to a compact, self-contained modular footprint that fits directly inside a hospital's parking complex or auxiliary utility building. By substituting tap water with liquid salt matrices, Chinese engineers bypassed the greatest structural flaw of modern power generation. They created a closed-loop thermal engine that operates at extreme temperatures, zero internal pressure, and completely independent of external water supplies. But this breakthrough raises a fascinating, uncomfortable historical question. If liquid salt technology is so vastly superior to traditional steam generators, why didn't Western power companies build this decades ago? The answer leads straight back to a forgotten lab in Tennessee, and a fateful choice made by the American government that changed the course of energy history. The most shocking part of China's 50-year saltwater power generator is not that it exists today. The most shocking part is that the entire original blueprint for this technology was invented, built, and successfully operated right here in the United States nearly 60 years ago, and then completely discarded by the American government. To see how this happened, you have to go back to the 1960s, deep inside the oak-covered hills of Tennessee at Oak Ridge National Laboratory. A brilliant American nuclear physicist named Alvin Weinberg was leading a team of world-class scientists. Weinberg had already helped design the standard water-cooled nuclear reactors that power modern submarines and commercial plants. But he recognized early on that water-cooled reactors were inherently dangerous because of their immense internal pressure and reliance on massive water supplies. Weinberg wanted to build a reactor that could never melt down, required no high-pressure water pumps, and could run indefinitely on low-cost fuel. So, between 1965 and 1969, Weinberg's team built the molten-salt reactor experiment, known as the MSR. They melted fluoride salts, dissolved fuel directly into the liquid matrix, and ran the engine continuously for over 15,000 operational hours. The test was a resounding success. The liquid salt engine ran smoothly at high temperatures without pressure buildup. When scientists deliberately turned off the cooling fans and cut power to simulate a worst-case disaster scenario, the reactor did not explode or melt down. Instead, a plug of solid salt at the bottom of the vessel naturally melted, allowing the liquid fuel to drain by gravity into passive underground storage tanks, where it safely cooled down into solid stone without any human intervention. It was, by every technical measure, a revolutionary breakthrough for safe, clean, off-grid energy generation. Yet, in 1973, the U.S. Department of Energy ordered the Oak Ridge Molten Salt project to be completely shut down, its funding pulled, and its engineering files archived in boxes. Why would the United States government destroy its own working prototype of a zero-pressure, melt-proof energy generator? The answer came down to Cold War politics and military priorities. The Nixon administration was focused on producing weapons-grade plutonium for nuclear warheads and expanding the fast breeder reactor program in California. Standard solid uranium water reactors produced plutonium as a byproduct. Molten salt reactors did not. Liquid salt engines were too safe, too peaceful, and produced no material for bombs. Because molten salt could not be weaponized, Washington abandoned it. For nearly 40 years, those revolutionary American engineering papers sat quietly in federal archives, collecting dust while the U.S. power grid grew older, more fragile, and increasingly reliant on fossil fuels and aging water reactors. Then, in the early 2010s, the Chinese Academy of Sciences made a calculated move that passed almost entirely unnoticed by Western media. They digitized Alvin Weinberg's original Oak Ridge research reports, translated every formula, and launched a massive, state-funded initiative headquartered in Shanghai. Chinese leadership poured over $500 million and assigned hundreds of full-time nuclear and chemical engineers to take Weinberg's abandoned American blueprint and build a modern, commercial-scale production model. While Western energy executives dismissed liquid salt as an unproven textbook theory, Chinese state engineers spent a decade solving the material challenges that had limited Oak Ridge in the 1960s. They developed advanced nickel-chromium alloys that could resist liquid salt corrosion for half a century, integrated digital sensors, and refined the chemical processing loops. What is running today outside the city of Wuwei in Gansu Province is the direct descendant of American genius, born in Tennessee 6 decades ago. China did not invent liquid salt power generation from scratch. They simply picked up the blueprint that Washington threw in the trash, modernized it with 21st century materials, and turned it into a sovereign commercial technology. And as you are about to see, they didn't stop with thermal salt reactors. They paired it with an equally wild chemical saltwater breakthrough that changes emergency backup power forever. While China's liquid molten salt thermal generator solved the long-term 50-year baseload power equation, Chinese engineers faced a second critical challenge when designing power systems for off-grid hospitals: instantaneous activation. A thermal liquid salt generator delivers steady, high-capacity output, but warming a thermal matrix up to its optimal operating temperature takes time. If a hospital's central electrical line is cut by a sudden storm or physical disruption, critical medical equipment cannot afford a single minute of delay. To bridge that gap, Chinese researchers coupled their molten salt platforms with a second, equally disruptive innovation: seawater-activated aluminum air power cells. This chemical system represents a radical departure from traditional lithium-ion batteries or diesel starter engines, providing an immediate, non-degrading electrical current the second salt water touches its internal plates. Standard lithium-ion battery banks, like those used in modern electric vehicles or commercial grid storage systems, suffer from severe built-in limitations. They are expensive, prone to thermal runaway fires, and degrade continuously over time, even if they sit completely unused in a climate-controlled room. A massive lithium backup array installed in a hospital basement today will lose a significant portion of its total storage capacity after just 5 to 8 years, requiring multi-million-dollar replacement cycles. Aluminum air seawater cells operate on a totally different chemical principle. Inside the unit sit lightweight, ultra-dense plates of alloyed aluminum, positioned opposite porous carbon cathode plates. Under dry conditions, the system is completely inert. There is no self-discharge, no chemical degradation, and zero risk of fire or leakage. The battery can sit in a dry, unpowered storage vault for 20, 30, or even 40 years without losing a single percentage point of its original energy potential. The magic happens when salt water enters the reaction chamber. The moment seawater or a basic saline solution is pumped into the cell array, the salt water acts as an active electrolyte. Oxygen from the surrounding air reacts with the wet aluminum plates, releasing a massive, continuous stream of free electrons that flow directly into the hospital's electrical panel. The energy density of this reaction is staggering. Aluminum air chemical cells achieve an energy density nearly 8 times higher than the best lithium-ion batteries available on the market today. A compact aluminum-seawater array occupying the footprint of a standard office desk can generate enough instantaneous high-voltage current to power an entire hospital intensive care unit, surgical lighting grid, and central cooling loop while the main liquid salt thermal system ramps up to full operating capacity. Because the system relies on seawater and solid aluminum plates, there are no toxic heavy metals, no rare cobalt supplies, and no expensive chemical stabilizers required. Once the reaction runs its course, the byproduct is simple aluminum hydroxide, a non-toxic substance widely used in everyday products, like toothpaste and antacids, which can easily be recycled back into fresh metal plates. By integrating seawater-activated aluminum cells directly alongside their long-duration liquid molten salt matrices, Chinese engineers created a two-stage, totally self-contained power architecture. Stage 1 provides immediate, zero-delay emergency electricity triggered by basic salt water, while Stage 2 delivers continuous, high-efficiency thermal power for up to 50 years. This dual-layer system eliminates every single point of failure that currently plagues Western hospital backup grids. There are no diesel engine pistons to freeze, no stored fuel supplies to rot into sludge, and no fragile lithium battery packs to degrade or catch fire. It is an unjammable, zero-maintenance energy fortress. And as Western industrial executives are beginning to realize, the technology born in these hospital power bays is about to spill over into the global commercial market, threatening some of America's biggest industrial giants. When news of China's 50-year saltwater power platform began spreading through global engineering circles, the initial reaction from Detroit, Silicon Valley, and Wall Street was quiet skepticism. For decades, American industrial conglomerates have controlled the global market for emergency backup power and microgrid equipment. Companies like Caterpillar, Cummins, General Electric, and Tesla generate tens of billions of dollars every single year selling heavy diesel generators, natural gas turbines, and lithium-ion megapacks to hospitals, military installations, data centers, and municipal utilities around the world. That massive business model relies on a simple, repeating revenue loop. You sell a facility an expensive generator or battery bank today, and then you charge them continuous subscription-style fees for the next 30 years. Mandatory routine maintenance contracts, replacement parts, software updates, fuel treatment chemicals, and total battery pack replacements every decade. China's non-pressurized liquid salt and seawater-activated power platforms completely destroy that business model. If a hospital, remote research facility, or commercial data center can install a self-contained, zero-maintenance salt power unit that operates reliably for 50 years without requiring petroleum shipments or frequent battery swaps, the economic appeal of traditional Western backup systems evaporates almost overnight. Consider the implications for Silicon Valley's booming artificial intelligence industry. The massive data centers built by tech giants like Google, Microsoft, and Amazon require gargantuan amounts of continuous, uninterrupted electricity. Currently, these tech hubs are stretching regional U.S. power grids to their absolute breaking point, forcing tech companies to build giant fields of diesel generators and short lifespan battery banks just to prevent catastrophic server blackouts. A compact, off-grid liquid salt platform provides the exact kind of high-density, 24/7 baseload power that AI server farms desperately need to stay competitive. The defense sector is paying even closer attention. The U.S. Department of Defense operates hundreds of forward operating bases, naval stations, and remote radar installations across the globe. Keeping those bases powered requires continuous, highly vulnerable supply convoys carrying millions of gallons of diesel fuel through hostile territory. A zero-fuel, seawater-activated power platform that can sit dormant for decades and run critical military systems without an external supply chain changes the fundamental math of logistics and geopolitical defense. Yet, while Chinese state enterprises like the Shanghai Institute of Applied Physics are rapidly commercializing molten salt modular systems for export across Asia, Africa, and the Middle East, Western manufacturers remain largely stuck in regulatory red tape and legacy supply chains. American power companies are heavily invested in existing water-cooled infrastructure, making it nearly impossible for domestic startups to get approval for non-water liquid salt designs. The gap between East and West is no longer just about who builds the fastest electric car or the smartest AI chatbot. It is about who controls the underlying energy architecture that keeps critical modern civilization running during a global crisis. China has recognized that the future of power belongs to systems that are decentralized, physically invulnerable, and independent of traditional fuel grids. By taking American technology abandoned in the Cold War and scaling it with seawater chemistry, they are positioning themselves to dominate the global microgrid market for the next half-century, and leaving traditional Western equipment makers fighting over an obsolete past. What began as a sensational viral headline about a hospital running on salt water for 50 years reveals a much deeper, far more urgent truth about the future of global energy. The internet simplified the story into a catchy illusion, but the physical reality unfolding inside places like Gansu Province is vastly more important than any viral video clip. China has shown the world that the ultimate goal of modern power engineering is not just building bigger solar installations or digging larger lithium mines. It is achieving total, un-jammable energy sovereignty for critical human infrastructure. For over a century, the Western world operated on a comfortable assumption that central power grids would always remain stable, that fossil fuel supply chains would never break, and that American technology would forever dictate the terms of global innovation. We built giant, hyper-complex electrical grids that work brilliantly when the weather is calm and the geopolitical environment is peaceful. But the moment a major hurricane hits, a freeze paralyzes fuel pipelines, or an international crisis disrupts shipping lanes, that magnificent infrastructure reveals its extreme fragility. The saltwater breakthrough in China represents a completely different philosophy of survival. By combining low-pressure liquid molten salt thermal engines with seawater-activated chemical power cells, engineers have unlocked a way to decouple society's most vital facilities: hospitals, emergency centers, water treatment plants, and communications hubs, from vulnerable municipal grids and fragile oil routes. They built a system where the laws of physics and chemistry themselves guarantee continuous power for half a century, with zero dependence on fuel trucks, external water pipes, or foreign supply chains. The tragic irony of this moment is that the foundational science powering China's off-grid miracle was originally designed by American minds in Tennessee nearly 60 years ago. The United States had the chance to lead the liquid salt revolution, to build ultra-safe, non-pressurized power generators, and to secure its critical infrastructure against blackouts for generations. But short-term political priorities and legacy industry lobbying caused Washington to lock those blueprints in a vault and forget about them. China did not forget. They took America's discarded innovation, refined it with modern material science, paired it with advanced seawater chemistry, and built the world's first working commercial platforms. Today, while Western cities struggle with aging power grids and short-term battery solutions that degrade in less than a decade, Chinese engineers are exporting long-duration, off-grid energy platforms across the developing world. This is the new law of global power. The countries and companies that survive the next 50 years will not be those with the most complex, fragile networks. They will be those that build self-contained, resilient infrastructure capable of standing completely on its own when everything else around it fails. If a simple hospital in regional China can now sit safely off-grid, powered continuously for 50 years by the strange chemistry of salt water, it forces a direct question upon every American viewer watching this today. How long can your local hospital, your neighborhood grid, or your city stay dark before everything stops working? The technology to fix that problem was invented in America over half a century ago. The only question left is whether the West will wake up and rebuild its own power systems, or continue to